this whole section now that we're going to look at, 17.2 and 17.3 actually, are both heavy mathematical. Okay? So we looked at the basic ideas of electric charge in 17.1, and if you remember, that was all conceptual, right? We talked about induction, we talked about what the charge is, we talked about polarization, we talked about charging by contact, all those different things. Now, in this section, what we're going to start doing is calculating things to help us understand like what something really is or what its magnitude is. So we're going to use something called Coulomb's law, and as you notice, the same word as yesterday, remember, or the other day, for 17.1. The charge on a particle is measured in coulombs, okay? And again, Coulomb's law. And then we're going to compare, and this was James, right? You asked this the other day? We're going to compare the relative force between electric and gravitational force, between like a proton and an electron, to see how the electric force is actually a lot stronger than the gravitational force. Okay? Let's start by looking at the actual law. It's an equation really, but it's called Coulomb's law. Just like Snell's law is an equation, but it's called Snell's law. So what does this make you think of right away, before I even go any further? Yes, we can. Gotcha. Thanks, guys. What does this make you think of? Exactly. Think back to gravitational force. Wasn't it Gmm over r squared? Remember Gm1, m2 over r squared? Doesn't that look quite familiar? Instead of G, it's K. And we'll talk about what K is. It says it right there, actually. And then Q1 and Q2, what do you suspect those are? A quantity, okay. It is a quantity, but it's not standing for quantity. Good guess, though. I would think that. Remember with gravitational force, it was mass times mass. What affects the amount of pull between two things?
Attraction.
Okay, the attraction, good.
Electrons.
Number of electrons, okay.
Charge.
The charge. Number of electrons or charge. You said charge? So the charge on each of the particles. So, if we remember, M stood for mass, right? M stood for mass. Let's get these notes out, folks, if you don't have them out. M stood for mass. Now, Q is going to stand for charge in this case. And if there's more charge on a particle, there's going to be more force that exists. Now, if both of those charges are positive, then it's a repulsive force. They're pushing apart. If they're opposite charges, they're pulling together. Okay, so in this case, for these problems, when we calculate the force, the sign matters. The sign matters. Okay, if we end up having a positive times a positive, because we're having two positive charges, we're going to get a positive answer. Well, that means that they're actually repelling each other in this case. So we're going to talk about how that works when it comes to math.
If it's a negative force, it's like they're being drawn towards each other.
If it's a negative and a positive, you'll get a negative answer, and that's as if they're being pulled together.
Like the,
So
like the distance decreasing.
Sure.
Together.
You can think of it that way, absolutely.
I thought the Coulomb was not.
Now this is Coulomb's constant. This is not the elementary charge from the other day. The other day, 1.6 times 10 to the negative 19 coulombs. That's the elementary charge. This is Coulomb's constant, though. Okay? This is just like, remember big G? 6.67 times 10 to the negative 11? You used it in this formula where it was like G, M1, M2 over R squared. It's the same thing. It's just a constant. It's called a constant of proportionality, really. It's an experimentally determined value that is then verified with more, I don't know, high-tech stuff that we have now. But this number has been around for a long time. It's not something that they figured out with a lot of the machinery that we have or the electronics. It's a quite large number, you'll see, 9 times 10 to the positive 9. The reason being is because the Q values are most likely going to be very small, and you're going to see there's going to be a balance there. Okay, the charge values are not going to be on high orders. So this to the 9th power. Okay. Which section is this? 17.2. Q1 and Q2 are the charges on particles 1 and particle 2. Or particle 1 and particle 2.
So why are they called Q?
I don't know. Look it up. I'm not sure.
It's like,
Usually Q means heat. Capital Q, Q equals MC delta T from chemistry is heat. So I'm not sure what little q is charge. Can you check?
okay.
Thanks. And then R is the average distance between the particles. The average distance between the particles. Now, in these problems, remember how R for the gravitational force was the distance from center to center? And we had to consider the fact that the particle or the Earth had a radius, and that would change the distance. So if we have something like this, where the Earth is over here, and the moon was over here. We wanted to find the distance between them. We said that r was the distance from here to here. That's when we did gravitational force. Now, for a lot of these problems, what we're going to notice is that the radius of the proton or the electron or the charged particle has no effect on the problem because it's so small. So for the most part, you're going to just be given a distance between them in these problems. You're not going to have to worry about adding in the radii plus the actual gap. Okay, remember in this case, the r value for gravitational force would have been whatever this radius is, plus that gap, plus this radius. For these problems, this r is just the distance between the two. It's not going to be like center to center. You're not going to have to worry about calculating and adding in the radii. Okay? Again, the reason you can do that is because it's negligible. What does that mean again? What does it mean again?
Small, big.
Yeah, it has no significance. It's too small to have any effect on the problem. Okay? It has no significance whatsoever. Let's take a look at example 1. A simple example. Okay, a simple example. But this is really good because this allows us to relate relate gravitational force and electric force. So using the table below, I don't know where I wrote above. What did I write above? Let's just say below. Using the table below, determine the electric and gravitational forces experienced between an electron and a proton of a hydrogen atom. How many protons are in a hydrogen atom? Luke? One. Yeah, it's just one. So it's a proton, okay, a hydrogen atom. There's an electron in the nucleus. Is there a neutron in a hydrogen atom?
No, it can't.
I think it's just a proton and electron. I think it's serious. I think its atomic mass is just actually 1. I don't think there is a neutron in there. Anyhow, doesn't matter. So we want to find out the gravitational force between electron and proton, and also want to find out the electric force if the average distance between them is this quantity. And again, we're not going to include the radii here for these cases because they're such small values that they're negligible. So this is our R value. Let's calculate the electric force first, because we know that formula we just saw it a second ago. Okay, so we're going to use the formula with Kc Q1 Q2 over R squared. Well, here's your Q1. Here's your Q2. Okay? Kc is given, and then the distance between them is given in the actual problem up here. So, let's go ahead and plug these in. It's a direct substitution. There's no need to rearrange the formula at all. That's the nice part about this example here. Again, so it's K, which is 9 times 10 to the 9th. The units here are newtons meters squared per coulomb squared. I'm going to write them for this example so you can see that the units do balance out. So K times Q1, and that's in coulombs, times Q2, which is really the same number because protons and electrons have the same charge, but one is negative and one is positive. That's all that matters for this. So it's still, again, 1.6 times 10 to the 19, that's in coulombs, all over the distance between them squared. And take a look at your units right away, before we even calculate. I've got coulomb canceling with coulomb squared. Then, I've got meters squared up top here, and I've got meters squared in the bottom. Those are going to cancel each other, leaving behind only newtons. And what should our units be? Newtons, because we're calculating a force. We're calculating electric force. The units have got to be newtons. So the numbers do make sense, okay? Now, what do you need to use here? Yeah, or a calculator, please, okay? Have your calculator. So take it out and go ahead and practice this. Come up with your number. Make sure that you get it. Please don't just assume everybody else is getting it. Now, be careful here, because you have to divide by the denominator squared. So, think about how you're going to do that. Use your parentheses wisely. Save that in the Oh, wait, guys, they're both negative 19. Sorry, that's a typo. Thank you, Tristan. Or not a typo, but whatever. Both of these powers are negative 19. It should say negative 19 over here on the right.
Wait, but is it a positive 1.6?
Yeah. So it's positive 1.6, but that should have said negative 19 right there. Thank you, Tristan. Now remember, you're dividing by something here in the bottom that's going to be a very small number. So dividing by this is actually going to jack up the value of the answer.
I got an answer. Good job, Louis. I'm proud of you. What?
Did you do this last time?
Or something like that.
What you got?
8.2.
You get the same thing?
Yeah.
That's good. That's a good sign.
That's crazy.
I got something wrong.
I got negative 4.3.
Yeah, that's what I got. Wait, Tristan, what'd you get?
Negative 4.347.
Yeah, I got standing as Tristan.
It's not what I got. I got what these two got over here.
maybe it's wrong.
Negative 8.2 times 10 to the negative 8 newtons.
Yeah.
Let's go through this, because everybody's probably making the same mistake if the four of you got the same answer. So let's go through it. Lou,
Yeah.
tell me, listen folks, Lou, tell me how you type this in your calculator. Go step. God bless you. Those listening, do what Lou's saying. Step by step, he's going to tell you how he typed it in, and I want to see if it's any different from what you guys got.
Okay, so I started off with the numerator, and I typed them all in. I did parentheses 9, either 9, close parentheses, the next one, and then parentheses the next one.
All right, so numerator first. Everybody do that. Hold on. Did you hit enter after that or no?
Are you using E?
Yes.
Lou, did you hit enter after that?
Yes.
So let's all do the numerator together. Okay, multiply these three quantities up top. Hit enter and see what you get as your answer. I have a feeling for the denominator we forgot some parentheses, so that's my guess as to what it is. But let's see. What did you get as an intermediate step there? Do you know?
Yeah, 2.3 times 10 to the negative.
Negative 2.304 times
10 to the negative 20.
28.
Yeah, okay, is that the intermediate? Good. Now, everybody hit divide.
Oh,
Right?
I didn't divide it.
Oh, you didn't do it yet?
I did.
Did you find the next number and then divide it 2?
Yeah.
Okay.
That's what it is.
I'm going to say do this though. Hit divide. Hit open parentheses. Open parentheses. So twice. 5.3, whatever the number is. E negative 11.
I forgot to square.
Close parentheses. Square it. Then close parentheses again.
Yeah, I forgot to square it too.
Forgot to square it? Tristan?
Oh, yeah.
Okay. Do we all get the right answer now at this point?
Okay,
No?
I know what I did. It's a,
Oh, but you know you did wrong?
Negative 8.2.
What was it?
Negative 8.2 times 10 to the negative 8.
Oh. Wait, so.
Yeah, I got negative 8.
How did you find
I got negative 4.3.
You didn't square the denominator.
there we go.
That's what they got earlier when they forgot to square the denominator here. Alright, now what I want to do is finish the problem and calculate the gravitational force between a proton and an electron. How do you find the gravitational force? What's that formula, Julian?
Gravitation. Well, I just have a quick question.
Go ahead.
So I got the same exact number, but my exponent is like negative 52.
That means that you probably forgot the negative 19s in the numerator. Are they both? Did you forget the negative 19? Check all of your exponents. Something's wrong somewhere along the way.
Okay. And the gravitational is like the Fg equals big G, right? And then R squared at bottom. M1.
Yeah. So again, analogous or similar, right, to the last one. Remember how when we found the period, it was 2 pi root L over G or 2 pi root M over K. Remember that? Those formulas are very similar, just like these are. Electric force, gravitational force, very similar formulas. Now, you're given the masses in that table. Big G is given at 6.67 times 10 to the negative 11. R is the same value as the previous part, because we're still looking at this proton and this electron separated by this given distance. And if we go ahead and plug these numbers in, what we're going to end up getting is 3.6 times 10 to the negative 47. Now, that's in newtons, obviously, as well. And take a look at the huge difference here. We can clearly see that the electric force felt between them, the attractive force, that's why this negative is here, is much greater, or a much greater scale, or a much greater magnitude than the gravitational force felt, something to the negative 47th power. That's a tiny, tiny amount of gravitational force, whereas the electric force, although small, is much greater than the gravitational force. Switch to F and the R squared, and then square root it. Yep, absolutely. So Tristan already noticed, he said, you know what, these are inversely related. By the way, notice I put the K in the numerator now, instead of in front. It doesn't matter. It's still a oh, it's not on the board. Hold on. So it doesn't matter whether it's in the numerator or on front, it's still a multiplier. So as Tristan said, let's flip-flop the R squared and the FE, and then take the square root. So start by putting R squared up here and write it as K Q1 Q2 over the electric force. And then just put a square root, and it gets rid of that squared there. So that's going to be our generic solution for this problem. We're trying to find the distance between these 2 point charges. A point charge just means a charge on a particle that is so small we consider it to be a point in space. Right? If I were to draw a simple dot, or think about like, you took geometry last year. Remember, one-dimensional is a point, 2 dimensions is a line, or is a plane. 3 dimensions is a rectangular object or a prism. Sorry, a point is no dimensions. A line is 1 dimension. A plane is 2 dimensions, and then a figure is 3 dimensions. A point has no dimension to it. So when you hear a point or a point charge, think about like there's a charge in space on a particle, but the particle is so small that everything else doesn't matter, like the mass and stuff. Okay, it's a really infinitesimally small particle. So we know Q1 and Q2, but what should we do? For Q1 and Q2 in this problem, what do we have to do? Look at the units and look at the prefix. How do I have to write it?
Wait, no. Sorry, you have to move to the temperature. Right?
Bring them down.
I was thinking.
Now we're given the charge in this one. Bless you. Remember in the last problem we canceled all of our units and showed that there was a balance of units? Everybody remember that? No? In the last problem, we showed all the units, how the newtons meter squared cancel with meter squared, coulombs cancel with coulombs. The problem was units were coulombs. What are the units here, though? Microcoulombs. Good, Nina. Microcoulombs. So we can't use microcoulombs because they're not going to work. We need to have coulombs, like the last problem. So what should we do?
Times 1,000.
Not 1,000.
Times
Million.
10 to the...
Negative 6.
Yeah, what I said before, that was micro, negative 6. So Q1 is really this. And Q2 is this. Okay? So please, just like we did with, what was it? Wavelengths. Remember wavelengths, some of them were given in like nanometers, and you have to multiply times 10 to the negative 9. Or frequency was in gigahertz, or megahertz, or kilohertz. And we have to change that. Same thing here. It's got to be in your base unit. So get rid of that micro by putting 10 to the negative 6 there. Now, these numbers clearly are going to go right into the formula. K is given, 9 times 10 to the positive 9. Fe is given as 150. Before you take a quick break, Fe is a repulsive force. We're going to have a positive in the top, a positive, and then a positive. These are all positives. What about this denominator? What should it be? Which one?
Positive, because it's a repulsive.
Positive because it's a... Okay, if in the case it had been an attractive force, what do I have to do? Yeah, you have to apply negative, and you'll see that because look, if this were the case where it was an attractive force, wouldn't one of the Q's be negative?
Yeah.
Making the numerator negative? And you can't have a negative under the radical, else it's imaginary, right? So if there's a negative in one of the Q's, then Fe is most definitely negative. And those negatives cancel, making this a positive under the radical, so you can actually get a distance. Because if you took a square root and there was a negative under it, it would be an imaginary distance. Okay? Take a quick 3-minute break. So to reiterate one more time, the force is repulsion, so it's a positive force we get, and these Q values are both positive, so it's all positives under the radical, which is what we need. Whenever you find something under a square root in this class, it's got to be a positive number, because you're looking for a real answer, not an imaginary answer. So if one of these Q's had been negative, it would be a force of attraction. That would make one of the Q's negative, but would also make the force negative, showing attraction. Negative and negative would cancel, still being positive. Okay, so let's plug in. Let's plug in. We've got the square root of 9 times 10 to the 9, 50 times 10 to the negative 6, 40 times 10 to the negative 6, all over 150. Your answer is obviously in meters, because we have all standard units here. Check it out, let's go. Type it in, try it. A lot of you made mistakes in the last one, you need to practice.
0.346?
Maybe. Hey, he's the first one to it, I'm glad. Others can verify.
What did you say? 0.346?
Tristan, let's go. Calculator, check it. Nick, what was it? 346? Yeah. I wrote 3.5 because I rounded it. 0.346 meters.
Did I not get this right?
I hope you got it right, Lise.
Yes, you got 3.4.
Now,
Times negative 10.
Okay, you got it.
Times negative 10?
I mean like E negative 10.
Times 10 to the negative 1.
Oh, times 10 to the negative 1.
No, times negative 10.
Times 10 to the negative 1.
That's not what it says.
It says E negative 10.
It says E negative
and
10?
that's 10 to the negative 10.
So it means you typed something wrong. Go back and look.
My bad.
Check it again. It's probably one of your powers was typed in wrong if you have the right base number, right? You got 346 still? But it's off?
0.46.
Yeah, so it means that one of your powers was wrong along the way. Did you make this a 9 and a negative 6 or a negative 6?
I made that a negative 9.
That's why. There you go. Okay, and you can tell that because the 3.46 was still there, which means that just one of your exponents is wrong.
So
You see what I'm
if I
saying?
took it on a test,
You should right away say to yourself, well, I mean, you wouldn't know what the right answer was on a test.
yeah, so like, would I get that completely wrong?
No. Depends on what you write.
Alright.
If you have the generic solution, I usually give most credit. Then you show the substitution and then the answer. Any questions on this one? Can we move on? Okay, we have one more example to do, but it's going to take us a while. Okay, it's going to take us a while. I want to talk about some things first, then we'll do that last example. So some key ideas that concern electric force. First, it is a field force. It is a field force like gravity. What is friction considered to be? A contact force, because you can't have friction without some contact, right? There's no friction if there's no contact. Obviously, air is contact to my hands, so there's friction there. But between my hands, there can only be friction if there's contact. Whereas the electric force, like gravity, is a field force. You don't see it. You don't actually, it's not tangible to you. Okay, it's not like you're like, oh wow, look at the gravity around me, it's pulling me down. You feel it, but you don't actually see it, right? It's analogous to the gravitational force, which is what we mentioned in the beginning. It's analogous to GMM over R squared. Instead, it's KQQ over R squared. Third, it can repel or attract, whereas gravity can only attract. Okay, because mass is always positive with gravity. Gravity is always attractive force. And the last one, it is significantly stronger than the gravitational force. All right, let's go on to the next part. Example 3 is a tricky one. Example 3 is a tricky one. Okay, because now we have 3 particles. And the formula clearly doesn't have Q1, Q2, and Q3 in it, right? So we're not going to be able to use the formula directly. We're going to have to do some changes, or do have some, take a roundabout approach. So we're told that 3 charged particles are arranged in a line. So start by thinking about where they are. Particle 1 is located, and the charges don't worry about for now. We'll label them in a minute. But it's located 0.3 of a meter to the left of particle 2. And then particle 2, which is located 0.2 meters to the left of particle 3. So let's draw it. Well, here's particle 1. Here's particle 2. And here's now particle 3. And I'm going to try and draw them to scale. Okay, this gap here is the 0.3 meters. And this gap is 0.2 meters. This is Q1, and that's equal to negative 8 times 10 to the negative 6 coulombs. This is Q2, which is 3 times 10 to the negative 6 coulombs. And this is Q3, negative 4 times 10 to the negative 6 coulombs. All right. Now, just by inspection, without math, just by looking, can somebody give me a piece of information about what is going on here? Looking at the distances, the signs, the positives, the negatives, what's happening in this problem? What could you physically see happening just from the setup, without any math? Just
Number 2, number 3 are going to track.
absolutely, very good. 2 and 3 are opposite signs, aren't they? 2 is a positive charge, 3 is a negative charge. A negative and a positive have to attract. Very good. What else?
Could you, I was gonna say something. Could you like combine 2 of them?
That's what we're going to do in a minute, yep.
Oh,
That's what we're going to look at. We're going to see a way of combining their overall forces felt. Not their charges, though, but their forces. But we're going to combine them. So Tristan said 2 and 3 attract. What about 1 and 2?
They're not going to try.
They also attract. It's negative and a positive. But 1 and 3, what do? They are repulsive, 1 and 3. So there's a lot going on here, isn't there? So the question is the attractive force bigger than the repulsive force, really? Which of these forces is greatest? So what might be useful to draw? A what diagram?
Free body diagram.
Yeah, an FBD. And we are really concerned. FBD, free body diagram. I don't want to know what that means. So we want to determine the net electrostatic force. The electrostatic force on the third particle. On the third particle. So everybody, please draw. Stop, come on. Draw the third particle by itself down here. And here's what I want you to think about. This is where it's getting a little bit tricky. All I want you to do is draw what you would think of as a free body diagram. What forces are acting on this particle and in what direction? So the arrows matter. So think of this as your free body right here, that point in space, and show me on your paper or draw on your paper what you think the free body diagram would look like as a result of these other 2 particles. Okay, so what forces do we have acting on this? Don't even think about gravity. Okay, you don't have to draw weight acting down in this case. Okay? Again, you're drawing it on yours. Bless you. Take a minute and get an idea as to what you're going to draw here.
Carl, I don't like this stuff.
Why?
Grinding gears.
Kind of years. It's not as tangible as the other stuff.
Yeah.
Mechanics is so simple to see, whereas electricity and magnetism, it's like you don't see any of this stuff. You actually have to test it and use readers and voltmeters to see the results, but you physically can't always see it. When we get to magnetic force, and when we look at things like the fields between them and the actual forces felt, it's a little easier to see. With electric charge, it's a lot tougher.
Even the EM spectrum made more sense to me than this.
Even the EM spectrum,
Yeah, like.
because you can see it. It's something that's tangible. Again.
It is.
All right. With the sign of talking, let's take a look. What is what is particle 2 doing to particle 3? Lisa.
Pulling it
It is pulling it to the which way?
that way.
To the left. So let's draw an arrow like that and write down F32. A force on particle 3 due to particle 2. Not 32, but 32. Again, this is a force on particle 3 due to particle 2. James.
Can I put my own subscription to that one?
Sure, but I'm going to tell you that most textbooks in college use this subscript for it. So it makes sense to continue with that.
But I have a
Okay?
question. Is that really like F3 and then even like F little 3 and then even a literal?
No. It's just 32. Like it looks like the number 32, but it's said F32. You could put a comma between them if you like, if that helps. That's fine. Okay? What would the other one be, Clue?
F,
What direction?
oh, right?
Yeah, why is this one going to be to the right? Because,
It's getting pushed apart.
yeah, again, negative are repulsive. So charge 1 is going to push back against charge 3. Because the same signs repel. And what would it look like?
F31.
Yeah, the force on particle 3 due to particle 1. So, in reality, if we wanted to figure out what is happening or what force is felt by particle 3, we could simply look at these two forces, F32 being negative, F31 being positive. Okay? We don't really need to worry about the signs anymore because our free body diagram took that into account. Remember when I drew a free body diagram and weight acted down and we suddenly said little g doesn't need to be negative anymore because we already drew acting down and that took that into account already? Same thing here. So when you plug in Q1, Q2 over R squared, all that times Kc, and you got a force, don't worry about the negative signs and positive signs anymore for the Q values when you plug in, because the arrows tell you what you have. Alright, so let's go ahead and calculate F32 and F31. So let's calculate F32 first. And again, this is the force felt by particle 3 due to particle 2. So particle 2, it wants to pull it back. Here's particle 2, it's all positive in the middle here. Particle 3 is negative, it wants to pull it back toward it. So we've got K, Q1, Q2. So here's K, Q1, or in this case, it's not, K is a constant, it's given. That was in the previous slides. The Q's in this problem are really Q3 and Q2, right? Because we're looking at F32 here. So this is going to be right here. This is going to be like Q3, and this is going to be Q2, because we're using these two. When we do F31 in a minute afterward, we're going to use particle 3 and particle 1 as our charges. So particle 3, again, I'm ignoring the negative sign, because I've already taken it into account. So again, take a look up if it's confusing. This is Q3. This is Q2. I'm not putting the negative in front of the 4 there because I know already that this is pulling it back to the left. I've taken into account the fact that these are opposite signs in my free body diagram here showing an attractive force to the left. So I don't need the negative there. Is that clear what I'm saying right now? It's just like when we dropped the negative on little g when we looked at our free body diagrams. This is all over R squared. What is the distance between them? Yeah, 0.2 meters squared. Or 0.2 meters, that is the distance, and then let's square it. Okay, that will give us F32. What's the only real difference in F31?
The Q's?
And what else? There's one other thing.
The distance.
Yeah, the distance. F31, look at the distance here. That's the distance up top. What is that distance?
5 meters.
Yeah, 0.5 meters. That's going to be our distance. We're going to square that in the denominator. And then the Q's are a little bit different. We're still going to use F3. But now it's times Q3, but now it's times Q1. And again, I'm ignoring the signs on these charged particles here and here, here and here, because I've already taken into account my free body diagram. So the blue answer we're going to get is going to be a force pulling to the right. The red answer is going to be a force going to the left. So the blue answer in the end will be a positive. The red answer will be a negative. Okay, just for my free body diagram. That's what I'm getting that from. What do I get for these numbers? Anybody get for the first?
2.7.
Good. Units?
Uh,
Stop.
I forget.
I have really good ears. You guys know that. What's the second one going to be? Okay, what do we get for the second one? Check it out. Give it a minute. Anybody? Bueller. Anybody? We've seen Ferris Bueller?
Yes, of course.
Bueller. Bueller.
Terrence Bueller.
That looked like it really.
Oh, jeez.
Just kidding.
I was gonna say, that's a slap in the face. Yeah. 1.150. I got 1.2. I rounded, I guess.
Mark Howell, you're my hero.
Okay, I'm just gonna write 1.2 for the rounding, safe for now. Now, let's take a look. The red force here was pulling particle 3 back toward it. The blue force came from Q1 and that was pushing particle 3 away from it. Which of these is bigger?
After 2.
Yeah, clearly 2.7 is bigger than 1.2, right? And 2.7 is a pull. So what's going to happen is Q3 is going to feel a pull to the left. Let's take a look at what I'm saying here. If I want to find the net force, I look at my free body diagram. I remember that the net force on any object is the sum of the forces. F31 is acting to the right. F32 is acting to the left. Where am I getting the negative and positives? From up here. F31 was a pull to the right. That's positive, to the right. F32 was pulling it back. That's negative right there. So I end up doing 1.2 minus 2.7, giving me negative 1.5 newtons. So what does that mean? It means that the third particle is feeling a pull to the left. A pull to the left because it is negative. If this answer had been positive, it would be feeling that push to the right. So it's like, imagine if I were pushing on this desk, right, to the right, but at the same time, Lou was pushing to this direction, to the left. And if Lou pushed more than I did, it would end up moving to the left. That's what's happening here. F31 is the first particle wanting to push it over. F32 is the other particle pulling it back. Well, F32 happened to be bigger, so it's going to be pulled back in the end to the left. Hence, we have a negative sign here.
Are you going to do F31 minus F32, not the other way around?
Why didn't I do it the other way around? Look at the FBD at the top. F31 is to the right. Agreed? That's positive. So it gets a positive sign. F32 is to the left. So it gets a negative sign. I could have written it the other way around, but the signs have to carry with them. So it would look like this. If you wrote them the other way, it would look like this. But it's still the same answer, right? The negative F32 is negative because it's to the left. The F31 is positive because it's to the right. So the order doesn't matter as long as the negative and positive signs stay attached to those forces.
Wait, so you just add the 2 forces?
Sure. You just add the 2 forces. But if the force is negative, like F32 was, you have to apply a negative sign to it.
Yeah.
Okay? And that's what F net means. Right? Net means sum. Net force means the sum of the forces. So yes, you add them. But don't forget that negative sign there. All right? Let me pause there.